University, and it's my pleasure to chair the second session of this morning. We're starting a little later just to compensate for the slight overrun. And I have the pleasure to introduce Tobias Kolding. Tobias received his PhD from the University of Pennsylvania under Chris Croak and was at Courant Institute of New York University from 92 to 2008. And since 2005, he's been at MIT. In 2010, he received the Oswald Veblen Prize in Geometry with William Minicozzi for their work on minimal surfaces. And I think the talk today may cover some of that, possibly, or not. But in any case, it's a pleasure to have you, and take it away.
Well, thanks very much. So it's an honor to be here speaking at this conference. And so I want to talk about connections, so related to the talk of Yao and Rick. I want to talk about connections between geometry and PDEs. And my perspective would be slightly different than the two previous talks. My perspective is more using geometry to prove results in PDE. As opposed to the other way around. Okay, and so first I want to talk a little bit about the equations that we want to talk about. So optimal geometry and evolution of shapes are governed by PDEs. Geometric invariance makes the PDE canonical. And it means that the same type of equation appear over and over again across various fields. And it also means that the equation that may come initially from geometry, they also describe phenomena that are unrelated to geometry. So this is part of what makes these equations very natural. And so one of the themes here will be that the geometry unlock the structure, leading to fundamental tools in PDE. And understanding the equations require insights in both analysis and geometry and the interplay between these two. And so we'll see various examples of this. And I'm going to emphasize a few big ideas. Right, so obviously this is a relatively short talk, so I will just emphasize a few big ideas. I'll suppress many other interesting aspects and results, but I hope this will give you a taste of a large and very active area. And I'm going to focus on joint work with Bill Minicozzi. So the interplay between analysis and geometry that we will look at are in two examples. It's in optimal regularity in PDEs, and it is about stability of solutions. Right. So the second topic here is related to what Rick was in part talking about, and the first is more about regularity in PDEs. So in PDE, existence is often proven in a weak sense. So this could be in the distribution sense or in the viscosity sense. And so these are very general techniques that gives existence of solutions, but with very little information about the solutions. The challenge is then to prove regularity. Another challenge is that the natural PDEs are nonlinear, and this means that weak solutions, they might not be smooth. And when that happens, the question is how smooth are the solutions and how big is the singular set? The second theme, the second example that I will look at is stability of solutions. So in dynamics and PDE, a central question is what solutions are stable, which solutions are unstable. The stable ones are the ones that physically happen. The unstable solutions are not seen in nature. And so here we'll return to this. So this is indeed a catenoid that also appeared in Rick's talk. And what you see here in this picture is you see the catenoid as a subfilm, and it's like an evolution where it's a big enough piece of the catenoid that makes it unstable, and so it immediately pops and returns to a stable state. Okay. So a little bit more about the equation that we will talk about. So one comes from surface tension. So surface tension is a PDE. It gives a PDE that describes evolution of shape. Mean curvature is the force of surface tension. Surface tension causes water to form roughly spherical droplets. And so mean curvature is, so Rick talking about this. So mean curvature is if you take a surface, say in R3, and you take two planes, you intersect the surface with two planes, where the two plane is spanned by a vector that is tangent to the surface and one that is normal to it. So if you're looking at the geodesic curvature in all such two planes, so the geodesic curvature of the intersection of the surface with all such two planes, and you average the geodesic curvature, then you get the mean curvature. Later on, we will look at where the surface is the level set of a function. So you have a function u. Let's say that this is we're looking at a function on R3. And suppose that you're looking at the level set, let's say for the moment, although this will not in general be the case, but let's say that this is a regular value and you're looking at the level sets, then the gradient of u, right, is normal to the level set. And so this means that the unit normal is just one choice of unit normal is the gradient divided by the length of the gradient, right? And so the mean curvature then becomes just the divergence of the gradient. So this the mean curvature. One way of thinking about the mean curvature is that it's the divergence of the unit normal. And so this is the same as the divergence of the gradient of u divided by the norm of gradient of u. And so here it doesn't matter which divergence you are thinking about, whether you're thinking about the divergence on Euclidean space or you're thinking about the divergence on the level set. Okay. Let's give you the same result. Okay, so this is the mean curvature. The mean curvature is going to play an important role in the equation that we were looking at. As Rick was talking about, minimal surfaces, this is where the mean curvature is 0. So this means that if the surface tension is the only force acting, then you have equilibrium for a minimal surface. And so minimal surfaces have this long history going back to Euler in 1740 and Lagrange and the birth of calculus of variations in 1755. Right now, just because this is a talk that is celebrating the ICM in 1924 here in Canada, then it's worth noting that Hilbert's 19 problem, this was the birth of this was related to the birth of the highly successful regularities theorem, in part came out of Hilbert's 19 problem. So Hilbert 19 problem is one of the 23 problems that Hilbert stated at the ICM in Paris in 1900. And so slightly reformulated, what Hilbert asked was, what is the regularity of solutions in calculus of variations? And Hilbert mentioned in particular 4 equations. One is the Laplace equation, and another one is the minimal surface equation. And then he mentioned 2 other equations. So he was talking about what is the regularity of solutions that appear in calculus of variations. And so there have been, over the years, there have been a lot of work on this, going back to Bernstein in his thesis in 1904, work of the Georgi, Nash in the 50s, Moser, Giussi, Nierenberg, and many others starting in the 1960s and onward. So, right, okay, so one equation that, one natural equation that comes from geometry is the minimal surface equation, where the mean curvature is 0. Another natural equation is the mean curvature flow equation. So the mean curvature flow equation is when you don't have equilibrium. So if the surface tension is the only force acting, and you have equilibrium, then it's a minimal surface. If it's not in equilibrium, but to some extent going towards equilibrium, then you get the mean curvature flow equation. So a surface is evolving by, so here the schematic picture is the surface is the blue boundary here, and so the dark blue boundary. The light blue is just kind of the inside, but it's not actually the surface, right? The surface is illustrated by this simple closed curve. So the mean curvature flow is where the surface is evolving in time, and the speed that is evolving by is the mean curvature, and it's evolving normally to the surface. So the time derivative, it's a little bit more complicated than this, but I would just state it like this, that the time derivative of the position vector is minus the mean curvature times the unit normal, right? So remember that the mean curvature vector is the divergence of the unit normal. And so this is the mean curvature flow. And so it has the effect that if you have a convex point, this here point here is convex, then the surface at that point will be moving inward. Here you have a concave point. This here point is concave. The surface will move outward. Okay. Now, right, so now mean curvature flow, this also have a long history. It go back more than 100 years in mathematics and material science. In mathematics, it go back actually to the 1910s, teens at least. And in material science, there's reference to it in the literature already in the 1920s. That was long before material science existed as a field. And so one way of thinking about, well, first of all, the equation, the mean curvature flow equation, this is just like the minimal surface equation. It's a nonlinear equation. But unlike the minimal surface equation, that is an elliptic equation, then mean curvature flow is a nonlinear, it's a heat equation. It's based on the heat equation. So it's a nonlinear heat equation. And it is, you can think about it as the negative gradient flow for area on the infinite dimensional space of surfaces. So if you take a surface and you try to evolve, let's think about a surface in R3, and you try to evolve the surface so that the area locally decreases the fastest possible, then it is moving by the mean curvature flow. Okay. And so here is a simple example of, or maybe not so simple example, but it's an example that was analyzed a long time ago. It was analyzed in the early 1990s. It sits inside a family of rotational symmetric examples that was analyzed in the early 1990s by Engenen, Altshuler, and Giga. And so these are rotational symmetric, and this means that the PDE reduces to ODE. And you can use ODE methods. In particular, you can use Sturm-Liouville theorem that you have for one-dimensional heat equation, okay, to analyze this example. And so that's what they did. And so, so the example is that you take a dumbbell. So this is, again, the surface of a dumbbell. So you have here two bells, you have a neck connecting them. And you're looking at, so this is a time evolution starting here, going this way, and then continuing here. So you have first the dumbbell, and then under the mean curvature flow, what happened is that the neck here, the neck has much larger curvature, because the principal curvature around the neck is very large. You don't get much contribution across. But around you get a large contribution. So what you see in this example is that because the curvature of the neck is very large, then the neck will shrink off. It will pinch off first. The bell will shrink, but they won't shrink very much before the neck have actually pinched off. And so, so it has this, so this is kind of the reaction part of the equation that gives you that. The diffusion part of the equation gives you that once the neck has pinched off, then it will immediately become smooth. It will have very, very high curvature, but it will immediately become smooth. And it will, and in this example here, it will break into two components. Each of the two components will become rounder and rounder, and eventually they will become almost perfectly round, two spheres, and then they will disappear. So this is the evolution that happened. This example is often referred to as Gratian dumbbell, and again, if it sits inside this family where it's rotational and symmetric around an axis, so you can analyze it using one-dimensional heat equation methods. Okay. So that, of course, is very special. The other example, the other simple example I want to look at is actually even simpler. It's what often is referred to as a Merit ring. And this is a thin donut of revolution, so a thin torus of revolution. So that's the initial surface, and you're looking at the evolution of this. And because of the naturality of the equation, because it starts off as a surface of revolution, it will remain a surface of revolution under the flow. And it becomes extinct. In this case, it becomes extinct in a round circle. Okay, so we will see that these phenomena is typical in general later on. Okay, so we talked about a few equations. We talked about the minimal surface equation. We talked about the mean curvature flow equation. And I want to talk about another equation that comes from PDE. And so this is often used. So this is what's called the level set method. And so if you want to So geometrically, you're looking at you take a surface, you're looking at the evolution of that surface. If you now, and now as we saw with the Grayson dumbbell, when you're looking at the evolution, then you will hit the neck will at some point pinch off. That's a singularity. And then the flow will continue. But what does it mean that the flow continue, right? Because I define it in terms of the mean curvature. And right when it's singular, it's not, I mean, it's not well defined. The mean curvature is not well defined. So what does it at all mean that you continue the flow past that initial singularity for the dumbbell? Right? And so there's a way of making that. There's actually several ways of dealing with that. And I'll focus on one of these that is closely related to PDEs. There's two other methods. And the other methods that I won't discuss at all are one that is related to geometric method theory, and that go back to Braga. And the third one is a method of the Georgian. But I want to talk about the one that is connected with PDE and applied math. And so in this method, you think about so you have this surface. Let's say it's in R3. It doesn't need to be in R3. It could be a hypersurface in any Euclidean space. And so you think about this hypersurface now at the level set. Let's say as a zero level set of a function. And now you want to turn the geometric problem, that is something about the evolution of a surface. You want to turn this into a PDE that is something about a function on Euclidean space that satisfies some equation, right? And so what you do is that, so initially you just have this single surface that is evolving, and you're thinking about this surface as a zero level set of a function. But in order to get a PDE, you take this function that has this, so you have your initial surface, you choose a function that is, say, let's say negative inside the surface, zero on the surface, and positive outside. And now you require that not just that the zero level set evolved by the mean curvature flow, but that all of the level sets evolved by the mean curvature flow. That turn into a PDE on Euclidean space. This is the prototype of the level set method, right? This is like the poster boy of the level set method. And the level set methods has relatively long history. It was discussed in the physics literature already in the early 80s. And then it was it was extremely successful work on this by Sethian and Osher in the late 80s. And then there was more rigorous work that I'll come to in a minute, in the early 90s. And so, okay, so these here are is supposed to illustrate the level set method. Again, the poster boy for the level set methods is mean curvature flow evolution, but it has been used for many other phenomena, right? And this is again sort of part of this general theme that these equations that we try to analyze here, and one try in the sort of this whole general area of mathematics try to analyze, they come naturally, and therefore the problem that you are forced to deal with are natural problems that not just come in this area, but occur across a wide swath of areas. Okay, and so here, so again, right, so the level set methods, one of the advantages by the level set method is that it allows singularity and it allows topological changes. So I think I have, is that right? I have 5 minutes left, 6 minutes left.
No, I think you have 40 minutes.
Yeah. Okay. I think we started 5 minutes past, but okay, yeah. Okay, so okay, so now suppose we have so now I'm going to specialize to what's called monotone flows. So monotone flows is where you take where the evolution is moving where the evolution, so this was in the case of the dumbbell, gradient dumbbell, and also in the marriage ring. These are the, if you take the mean curvature flow in each of these two examples, it's going to move inward and it's keep moving inward. Okay, this corresponds to that the mean curvature is positive. Okay, now if that's the case, then you can turn the parabolic problem into an elliptic problem. And so this is what's called the arrival time function. And so the arrival time function is that because it's moving monotone inwards, then you're looking at a point in the domain. So suppose you're looking at this point, then the value of the function u is the time that the front arrive at that point. That's called the arrival time function. Okay. And so the arrival time function is defined on the domain that the initial front is bounding. Okay. And and here's illustrated in an example where again the outer one is the initial front. And so the arrival time function now it's again satisfying a nonlinear equation. So this is the equation that is satisfying this equation, is satisfying this equation. It's nonlinear. It's a degenerate equation. This is easier to see if you can rewrite this equation as the Laplacian minus the Hessian of the function in the double normal direction. If you write it like this, then it's clear that it's a degenerate equation. So it's nonlinear, it's degenerate. None of these things are great, but this is forced upon you. And the third thing that's even more problematic is that it's ill-defined when the gradient vanish. Right? You're forced to deal with the gradient vanish. This is correspond to that the level set becomes singular. Right? So you're forced to deal with that the function has points, critical points. Okay. And so that's the key. The key problem here is, what do you do about the critical points? So here is the arrival time function in two simple examples. So these are even, of course, even simpler than the examples I looked at. The two examples I looked at is the dumbbell and the marriage ring. But even simpler example would be to look at the mean curvature flow, where you take a round sphere and you're looking at the evolution of the round sphere. So this is to your left, where you see the different level sets, and to your right, you have the evolution of a round cylinder. And so in these two examples, for the arrival time function here, I normalized the arrival time function so that for the shrinking round spheres, they will become singular at time zero. I've normalized it so that it becomes singular at time zero, where it's just a point. Right? It has shrunk to a point. And so I've normalized them so that at the origin here, that's where it becomes extinct. Then this is the arrival time function for the round sphere. And in the case of the round cylinder, and I've again normalized it, I normalized it so that it becomes a line at time zero, and it becomes this line. Then this is the arrival time function. So you see that in both of these two very, very, very simple examples, you get a quadratic polynomial, and of course, it's you get a quadratic polynomial. The first case is maybe as far as a quadratic polynomial go, it's a little bit nicer than the second one because it's a non-degenerate. 0 is a non-degenerate critical point. In the second one, 0 is a degenerate critical point. Okay. So again, the arrival type function and the level set methods as a whole is central in applied mathematics. It has been studied numerically in extremely successful work by Osha and Sethia. It appears in various other fields. It also arises in game theory. The arrival time function arises in game theory, and it fits inside a larger family of natural PDEs. Now, existence. So what about existence and regularity? Right. So this is in the sort of spirit of Hilbert's 19 problem. What is the regularity of solutions that appear in calculus of variation? And so in the early 1990s, Evans, Brook, and independently Chen, Giga, and Goto, they proved existence. And they proved that, so they proved existence that in the viscosity sense, and they proved that solutions are Lipschitz. Okay, and the question is, the fundamental question is, how smooth are solutions? Is this the best you can do? Is that the solutions are Lipschitz? Is that the best you can do? And so Tom Illman in his thesis proved, so this is in the early 90s, proved that in general solutions are not C2. Okay, right, and so let me just remind you what viscosity solution, what is viscosity? So there's like two basic weak definitions of solutions. One is in the distribution sense, the other one is the one that is used here, and is in the viscosity sense. And so I'll just give you an idea of what viscosity sense means. So we say that a function is subharmonic in the viscosity sense. So U on Euclidean space is subharmonic at the origin in the viscosity sense. If there exists a smooth function V that is usually referred to as a barrier function that coincides with U at the origin, and it lies below U everywhere, or at least in the neighborhood of the origin, and the Laplacian of V is non-negative. So if there exists such a function, then this continuous function U is said to have Laplacian bigger or equal to 0 at 0, right? And so of course, if this holds everywhere, then we say that the function is subharmonic. And so, right, and the key for this, and there are variations of this, there's variation of this viscosity principle, and in fact, the one that is used here is a variation of this. It's not this. This one is really go back to Calabi, and the one that is used here is a variation of Pierre-Louis Lyon's and Mike Crandall. Okay. Right, but the key for the viscosity is that viscosity solutions satisfy the maximal principle. That's a key. Okay, and so an example of a viscosity, a function that is subharmonic in the viscosity sense, is the function on just the on the line. That is the norm of x. That is subharmonic in the viscosity sense, right? So you just need to, it's smooth everywhere except at the origin. And so you just need to check this at the origin, right? And that's clear, right? That the function constant equal to 0, that is a barrier. Okay. So now, okay, so now the theorem here is that from the work of Evans and Spook and Chen, Giga, and Goto, it was known that you have these solutions. There are solutions in the viscosity sense, and it was known that they are Lipschitz. But the theorem here is, and it was also known already in the early 90s, that solutions are not in general C2. And so the theorem here is that solutions to this nonlinear elliptic equation is twice differentiable everywhere. So not only is it C1, but actually, and not only is it C11, but actually the second derivative exists everywhere and is bounded actually, but it's not continuous, okay? And in fact, continuity of the second, that may seem like a somewhat esoteric analytic fact, that is actually a geometric statement. It's a strong geometric statement, continuity of the second derivative, okay? And so, in fact, so this is second theorem here, that if the arrival time is C2, it's C2 if and only if the entire front becomes singular at a single time, and then it becomes extinct. So you see that in the case of the marriage ring, this is exactly what happened, right? That it shrink and it becomes extinct in a round circle. In the case of the dumbbell, this is not what happened, right? The neck is pinching off first. That's one singular time. And then the two bells disappear later. That's another singular time. Of course, the bells could even have different size, and then you get three singular times. 5 minutes. Okay. Okay. So this illustrates, right, that so again the theorem here is that it's twice differentiable everywhere, and C2 actually have this geometric mean. Now let me, in the last 5 minutes, let me try to talk a little bit about how do we prove, and I won't even get to the second part of the talk, sorry. But let me talk about differentiability. So how do we prove differentiability? And so in order to prove differentiability, it's worth going all the way back to what is differentiability. Differentiability, right? If you have a function on the line, what does it mean that a function is differentiable at a point? That means that it looks like a linear function on all small scales, and it looks like the same linear function on even if you go on a smaller scale, it's the same linear function. It could not be a different linear function, right? And so this is what differentiability means. And so, of course, here's an example of something that is not differentiable. It does look like a line on all small scales, but as you go on a smaller and smaller scale, it looks like a different line. So this is the famous Holck curve. That was like the beginning of fractal curves. Okay. And so now, how do we prove differentiability? And so we look at, so the key here is, the key about this nonlinear equation is that it's ill-defined where the gradient vanishes. So where the gradient doesn't vanish, it's you can prove by classical methods that you get smoothness, right? So the key problem is where the gradient vanishes. And so I've normalized my function. I'm going to, I've normalized my function u. So I'm assuming that we're looking at that where the gradient vanishes is at the origin. And I'm also assuming that the value of the function is 0 at that point. I just normalize it like that. And now I define a sequence of rescalings. So these are the rescalings. Sorry, I don't know why it does this. But so these V lambda are the rescalings. And so the V lambda, they satisfy the same equation. And so in particular, if you get, and you have, right, if you start with a homogeneous quadratic polynomial, then this V lambda gives you the same polynomial. So you see in these two very simple examples where you're taking cylinders and sphere, then the arrival time function in those very simple examples, the arrival time function in both examples is a quadratic polynomial. So therefore, this V lambda is independent on lambda. Okay, now twice differentiability. This means that you have a second order Taylor expansion. And so we must show that this V lambda has a limit as lambda goes to 0. And so a priori, there's no reason to expect a limit, even for a subsequence. And so the key then becomes, does it give you a limit? And so right in the case of the Holck curve, you wouldn't get the corresponding thing would be not, it's not a quadratic polynomial, but if you do the sort of same at the first order, you wouldn't get the same line when you're blowing up. Okay, so I had to kind of skip. And so so it was, maybe I should just say that the level sets here were known already to be as you're blowing up, the level sets were known to be spheres or cylinders. The key is now, is it the same cylinder on different scales? Okay, and so this is a kind of well-known problem that occur across many fields in geometry and analysis. And this is the question of uniqueness of blowups. Okay, and so we proved that if you take a monotone flow and you do this sort of rescaling, then you always get a unique rescaling, right? And so this gives you, I'm just running out of time. So this gives you this gives you a second order Taylor expansion at all sufficiently small scales. Okay. And so this kind of questions about uniqueness of blowup have long been recognized as being fundamental in geometry. There's important work in the early 80s by Arngen and Allard for minimal varieties. And also even earlier in a different context, there's in the 1950s, where Shevich looked at analytic functions on Euclidean space. And he looked at gradient flows of analytic functions on Euclidean space, and he proved uniqueness of gradient flow trajectory for those. So this is the Wojciechowicz work led to important work in PDE and real algebraic geometry. Okay, so I know I'm basically out of time, and so right, so again, uniqueness of blowup implied that it looks like the same quadratic polynomial on all small scales. And so using uniqueness, so I'll just say that word and then I'll stop. And then I won't get to these results. I was going to talk about stability of solutions. But uniqueness, then once you have uniqueness of blowups, this also gives you strong information about the singular set.
So thanks for